Good afternoon, students. In the previous chapter, we studied about first order circuits, first order RC and RL circuits. In this chapter, we will study second order circuits, second order RLC circuits. We will see examples of second order RLC circuit, source-free series RLC circuit, source-free parallel RLC circuit, step response of a series RLC circuit, step response of a parallel RLC circuit, and general second order circuits. To start with, what is a second order circuit? A second order circuit is characterized by a second order differential equation. It consists of resistors and the equivalent of two energy storage elements, inductor and capacitor. Here, for example, we have a source, a second order circuit where we have a resistor, inductor, and capacitor, series RLC circuit, and here a parallel RLC circuit, resistor, capacitor, and inductor. Let's start with source-free series RLC circuit. The source-free series RLC circuit diagram is this one. We have a resistor, inductor, and capacitor. We have an initial current of an inductor, I0. Remember, the inductor current does not change abruptly. That means the inductor current at 0 plus is equal to at 0 minus. The voltage across the capacitor does not change abruptly. That means the voltage at 0 minus is equal to the voltage at 0 plus. So by applying KVL in this circuit, we have R times I, the voltage across the resistor, plus L di by dt, the voltage across the inductor, plus 1 over C, the integral of I dt from 0 to t, the voltage across the capacitor, is equal to 0. Now, if you see this equation, it is a mix of derivative and integration. So in order we have a differential equation, we do the derivative one more time of everything. When we do the derivative one more time, this will become R di by dt. This will become L second derivative of di by dt plus 1 over C. The derivative of the integration will cancel and we have I over C. So after rearranging, we have this equation. This is second order differential equation, and the parameter of interest is the current I through the circuit. Now, if we see this differential equation, we can write it. We can write the previous differential equation, this one, in terms of alpha and omega naught, like this. Second derivative of I to alpha di by dt plus omega naught square I is equal to 0. Alpha is R over 2L. Omega naught is the square root of 1 over LC. We can solve this equation if we have two initial conditions. The initial conditions are the current I at 0 and the derivative of I at 0. The current I at 0 means the initial current of the inductor, and di by d0, the derivative of the current d by dt of I at t equal to 0 is given by, from the KVL, we can get this equation, negative 1 over L times R I naught plus V naught in bracket, this one. So we can solve this equation by using these two initial conditions, and also by using alpha and omega naught. Now, we have three possible solutions for the second order for a differential equation. These are based on the relationship between alpha and omega naught. One, if alpha is greater than omega naught, we call it overdamped response. And we will have two real roots where the two real roots, we get it from this equation. S1 and S2 is equal to minus alpha plus of minus square root of alpha square minus omega naught square. Then the final solution is A1 S1t plus A2 e raised to S2t. And it looks like, the response looks like this curve. And if alpha is equal to omega naught, we call it critically damped. And the roots are equal, and the solution will be given by this formula. And if alpha less than omega naught, we call it underdamped response. And we'll have two complex roots, and the solution is I of t e raised to minus alpha t in bracket b1 cos omega dt plus b2 sine omega dt, where omega d is the square root of omega naught square minus alpha square. See, as you see from this, you'll have ringing effect or oscillation. Okay, it's damped. It is damped. It will be damped, and at t equals to infinity, of course, it will go to 0. So what are the unknowns from this solution? A1 and A2. A1 and A2, where we solve, where we get them from the initial conditions, I at 0 and the derivative of I at 0. So S1 and S2 are called natural frequencies because they are associated with the natural response of the circuit. Omega naught is called the resonant frequency or the undamped natural frequency, and alpha is called the damping factor. And alpha, the damping factor, depends on the resistance. So the presence of the resistance will create a damping effect. If R is equal to 0, then alpha will be equal to 0, and we will have an LC circuit with omega naught is equal to 1 over square root of LC. And of course, the oscillatory response of the oscillatory response of the circuit, as we see from the previous curve, this arises from the inductor and capacitor. One time the inductor transferring energy to the capacitor and the capacitor transferring energy to the inductor back and forth. So this creates oscillation. The critically damped case is the borderline between the underdamped and the overdamped case, and it decays fast. So if we want to have a shorter settling time, so the critically damped case is the better response. Okay, let's have example here. For example, if R equals to 10 ohm, L 5 Henry, C is equal to 2 millifarad, then let's find alpha and omega naught. Very simple. We just substitute the parameters. Alpha is 1, omega naught is 10. And because alpha is less than omega naught, this will have under damped response. Now let's have an example circuit here. In this circuit, find the current I of t. Assume that the circuit has reached steady state at t is equal to 0. That means if you see this circuit before t is equal to 0, the switch was closed. So the switch was closed, then the capacitor reaches steady state, the inductor reaches a steady state. That means the capacitor is open circuit and the inductor is short circuit. So in a steady state for t less than 0, the circuit looks like this. We have a 4 ohm resistor and a 6 ohm resistor in series. Therefore, the current I at 0 minus is equal to 10 volt over 4 plus 6 ohm 1 ampere. And the voltage across the capacitor V at 0 minus is equal to I at 0 times the 6 ohm. Why? Because the 6 ohm is in parallel with the capacitor. So they will have the same voltage. So we will have 6 volt. For t greater than 0, now the left part of the circuit will be out, and we will have the resistor 3 ohm, the capacitor, and the 6 ohm. So this will be a series RLC circuit. A series RLC circuit. So R is 9 ohms, 3 ohm plus 6 ohm, over 2L is equal to alpha equals to 9, and omega naught square root of 1 over LC is equal to 10. Since alpha is less than omega naught, then this is under damped situation. 9 is less than 10. So now we have the two roots, S1 and S2, given by this. We just replace alpha and omega naught, and we calculate. Then we calculate omega d. Omega d is equal to square root of omega naught square minus alpha square, which we get this one. Then the response is this one is under damped situation. So the under damped situation is e raised to minus alpha t plus a1 cos omega dt plus a2 sine omega dt, which is equal to e raised to minus 90 a1 cos omega dt plus a2. This is omega d. Now, how we get what is left A1 and A2? Where we get A1 and A2? From the initial conditions. I at 0 is 1 ampere. So we substitute in this equation T equals to 0, then A1 cosine 0, A2 sine 0, then we will get A1 is equal to 1. What about di by dt at T equals to 0? Di by dt at T equal to 0 is negative 1 over L R I at 0 plus V at 0. I at 0, we already have it. I at 0 already, it is 1 ampere. V at 0. Okay, V at 0 here is minus 6 volt. Why? Because originally, when we derived the series RLC circuit, this polarity was plus and this polarity was minus. But here V is 6 volt. Therefore, to make it similar to the original circuit, V at 0, the initial condition will be minus 6 volt. And we have now di by dt at t equal to 0 minus 6. Now we have the two initial conditions and two unknowns, a1 and a2. Then di by dt at t equal to 0 is given by this. And by replacing a1, 1, we get a2. Therefore, the final solution is this. This is a practice problem. You can be able to solve this. This is also a series RLC circuit. So find out the initial conditions and find the current I of t for t greater than 0. Okay, now source-free parallel RLC circuits. This is the parallel RLC circuit. This is the resistor. This is the inductor. This is the capacitor. So by taking this node, we can have, by applying KCL, IR plus IL plus IC is equal to 0. IR is V over R, the current through the resistor. IL is 1 over L, integration of the voltage. Note that they have the same voltage, they are in parallel all. So integration of the voltage plus IC C dV by dt. Again, this equation is a mix of integration and derivative. So we can remove the integration if we do one more time the derivative of everything. So if we do one more time the derivative of everything and rearrange, we get this differential equation. Second derivative of V by dt square plus 1 over RC dV by dt plus 1 over LC V is equal to 0. So again, this is a second order differential equation. The parameter is V, the voltage across the resistor, the inductor, and the capacitor. So we need the initial condition. One initial condition is V at 0, the capacitor voltage. And the other initial condition is dV by dt at t equals to 0. So if we write it in terms of alpha and omega naught, we can write it like this, where alpha is equal to 1 over 2 RC and omega naught 1 square root of 1 over LC. Now again, this has three possible solutions. If alpha greater than omega naught, overdamped case, and we will have two different roots, and then we have the solution a1 e to the power of s1t plus a2 e to the power of s2t. If alpha is equal to omega naught, we have the critically damped case, and the solution is given by this. And if alpha is less than omega naught, the underdamped case, and the solution given by this equation. Therefore, what is unknown from this all is A1 and A2, B1, B2, where we can solve them from the initial condition V at 0 and the derivative of V at 0. So how we get the derivative of V at 0 from the KCL? From the KCL, V naught over R plus I naught plus C dV naught by dt is equal to 0. So the derivative of the voltage by dV by dt at t equal to 0 will become is equal to minus of V naught plus Ri naught over Rc. Let's have this circuit. In this circuit, find the voltage V for t greater than 0. Assume that the initial voltage across the capacitor is 5 volt and the initial current of the inductor is 0. L is 1 Henry, C is 10 millifarad. This is millifarad, and R is 5 ohm. So what is the first step? The first step is to determine alpha and omega naught. Alpha is equal to 1 over 2 times RC. 2 times R is given by 5 ohm, and C is 10 millifarad. So 10 times 10 raised to minus 3, and alpha is 10. And omega naught 1 over square root of LC, substitute the L and C, we get 10. Therefore, if we compare alpha and omega naught, alpha is equal to omega naught. What kind of response we will get? We will get critically damped case. The solution for the critically damped is V of t is equal to A2 plus A1t, everything e to the power of minus alpha t. Okay, so we found alpha is this, alpha is 10, so we substitute and we have this. So what is unknown? A1 and A2. Where we get A1 and A2? From the initial conditions. Using the initial conditions, V at 0, for example. What is V at 0? V at 0 is a capacitor voltage. It's already given 5 volt. So substituting this equation, T is equal to 0. So T is equal to 0 means e to the power of 0. This is 0. So A2 will be 5. The second initial condition is the derivative of V by dt at t is equal to 0. This is equal to V at 0 plus R I at 0 over RC. So all are given. V at 0 is given. I at 0 is given. We substitute and we have the second initial condition dV by dt at 0 is minus 100. So we have two equations with two unknowns. What is this? This is simultaneous equation. So we can be able to solve this equation. So here dV by dt, when we do the derivative of this, okay, we have two functions. We take the rule of derivative for the product of two functions. If I have the product of two functions, f of t and g of t, the derivative of f of t times g of t is the derivative of f times g plus f times the derivative of g. So This is the first one, the first derivative of the derivative of a2 plus a1t is a1, and the e to the power of minus 10t, this is the second function, and the derivative of the second is minus 10 e to the power of minus 10t times a2 plus a1t. Then evaluate at t equal to 0, it will be a1 minus 10a2, and we have the initial condition minus 100, we substitute, and by this way we find the value of a2, the value of a1. So we substitute in the equation, and finally we'll get the voltage v of t given by this. Okay, this is a practice problem. Again, this is a parallel RLC circuit, and we need to be able to find v of t for t greater than 0. Remember that the steps to determine to find the solution is, first we need to determine alpha, and then we need to determine omega naught. We need to compare alpha and omega naught and determine if it is over damped, critically damped, and under damped, and then we use the initial conditions v at 0 and the derivative of the voltage at 0 to find the constants and finally the solution. I hope you understand source-free series RLC circuits and parallel RLC circuit. And in the next topic, we will discuss step response of series RLC circuit and parallel RL circuits. Thank you for listening to this lecture.